Have you ever wondered how data is structured and organized in a database system? Welcome to the fascinating world of data design. Data design, also known as database design or data modeling, is the art of defining the structure and organization of data within a database system. Think of it as the blueprint for your data's house, dictating how your data will live and interact within its environment. This process is crucial for ensuring data integrity, consistency, and accessibility throughout an application's lifecycle. The key aspects of data design include understanding and analyzing your data requirements, creating conceptual and logical data models, organizing your data through normalization and denormalization, and considering physical data modeling and data integrity constraints. We also need to think about how data will be accessed, queried, and manipulated by applications and users. Understanding data design can not only enhance your database management skills, but also help you design more efficient and effective database systems. Data design begins with understanding and analyzing the data requirements of the system or application. This initial step, known as data requirements analysis, is like drawing a map before embarking on a journey. It's about getting a clear picture of the types of data that will be stored. This could be anything from customer information for a retail application to complex scientific data for a research project. Then, we delve deeper to understand the relationships between these data types. How does one piece of data relate to another? What are the dependencies? What are the constraints? You see, it's not just about collecting data, it's about understanding how that data interconnects and interacts. We also examine the access patterns. Who will be using this data? How frequently? What kind of queries will they run? This helps us design a system that is not just efficient, but also user-friendly. In essence, a thorough data requirements analysis lays the foundation for a well-structured and efficient database system. The next step in data design involves conceptual and logical data modeling. Venturing into the realm of conceptual data modeling, we start by identifying high-level entities, attributes, and relationships within our system. This is where we get to the heart of our data, understanding the key elements and how they interact with each other. Conceptual data modeling isn't concerned with specifics of database technology, rather it focuses on representing the conceptual structure of the data. One popular technique used here is entity relationship modeling, or ER modeling for short. This method allows us to visually map out the main components of our data and the relationships between them. Once we've established our conceptual data model, we move on to logical data modeling. This stage is a bit like translating a novel from one language into another. We're taking the high-level overview provided by our conceptual model and translating it into a more detailed representation, which accounts for database implementation considerations. We start to define the logical structure of the data, naming our tables, columns, keys, and relationships. This is where relational modeling techniques come into play, helping us to structure our data in a way that's efficient and understandable. It's important to note that while conceptual and logical data modeling are two distinct stages in the data design process, they're also deeply interconnected. The logical model is, in essence, an extension of the conceptual model. It takes the abstract concepts identified in the conceptual stage and fleshes them out, adding the necessary detail to make them ready for implementation in a database system. In a nutshell, conceptual data modeling is all about identifying what our data looks like and how it relates to other data, while logical data modeling is about translating that understanding into a format that can be implemented in a database. Both conceptual and logical data modeling play crucial roles in representing and defining the structure of our data. Now let's delve into the concepts of normalization and denormalization. Normalization is a critical process in data design that focuses on organizing data within a database. Its primary purpose is to reduce redundancy and improve data integrity. Imagine you're organizing a library. Normalization is akin to categorizing books into genres, authors, and titles to ensure there are no duplicate copies, and that each book is easy to find. In the world of databases, normalization involves decomposing larger tables into smaller, more manageable entities. This process helps to eliminate data anomalies, such as update anomalies, insert anomalies, and delete anomalies. Update anomalies occur when we change data in one place, but forget to change it elsewhere, leading to inconsistent data. Insert anomalies happen when certain data cannot be inserted into the database due to missing attributes. Delete anomalies occur when deleting a specific record also removes other valuable data. After discussing normalization, let's pivot to denormalization. Denormalization is quite the opposite of normalization. It's the process of intentionally introducing redundancy into a database schema. Now you might be wondering, why would we want to reintroduce redundancy after going through the process of eliminating it? Well, denormalization serves a crucial purpose. It improves performance or simplifies query processing. Returning to our library analogy, denormalization would be like creating a separate section for most borrowed books or staff recommendations. While these books are already categorized elsewhere, having them in a separate section makes it quicker for readers to find popular or recommended books. Similarly, in databases, denormalization may involve storing redundant data or pre-calculating aggregated values to optimize query performance, especially for read-heavy workloads. However, it's important to note that both normalization and denormalization have their pros and cons. Normalization helps maintain data integrity and reduce redundancy, but it can lead to complex joins and slower query performance. On the other hand, denormalization can speed up queries, but at the cost of increased storage and potential data inconsistency. Striking a balance between normalization and denormalization can significantly impact database performance and efficiency. Once we've defined the logical structure of our data, we then transition into physical data modeling. This is where we connect the dots between our logical data model and the physical storage structures supported by the Database Management System, or DBMS. It's like creating a blueprint for a house, where the logical model is the concept, and the physical model is the construction plan with all the nitty-gritty details. In physical data modeling, we determine the physical implementation details such as storage formats, indexing strategies, partitioning schemes, and optimization settings. The goal here is to ensure that the database operates with optimum efficiency. For instance, we might decide to use a particular storage format because it's more space efficient, or we might choose a specific indexing strategy because it speeds up query performance. Partitioning schemes help us manage large volumes of data more effectively, while optimization settings allow us to fine-tune the DBMs for our specific needs. Every decision we make at this stage directly impacts the performance and scalability of our database. Now, as we're building our physical data model, we must also consider data integrity constraints. These are the rules and relationships we enforce within the database to maintain data consistency and accuracy. Without them, our database would be like a city without traffic laws, chaotic and accident-prone. There are several types of data integrity constraints. For example, primary key constraints ensure that each record in a table is unique. Foreign key constraints maintain the valid relationships between tables. Unique constraints prevent duplicate values in a column, and check constraints ensure that all values in a column meet certain criteria. Implementing these constraints is like setting up safety nets. They prevent us from making mistakes that could lead to data anomalies, such as duplicate records or inconsistent relationships. They ensure that our data remains reliable, accurate, and trustworthy. To sum up, physical data modeling is about turning our logical data model into a concrete plan for our database. It's about making strategic decisions that will maximize the performance and scalability of our database. And it's about implementing data integrity constraints to safeguard the accuracy and consistency of our data. A well-designed physical model and properly implemented data constraints ensure that our database is both efficient and reliable. Finally, we must consider data access patterns in our data design process. This is the magic that brings our data to life. Data access patterns are the ways in which data is accessed, queried, and manipulated by applications and users. These patterns give us an idea of how our data will be used, informing us on how to shape our database. It's all about efficiency and user-friendliness. To achieve this, we optimize the database schema and indexing strategies. The schema is the blueprint of our database, defining how data is organized. Indexing, on the other hand, speeds up data retrieval, making the database more responsive. We aim to support common access patterns and query requirements. This means our database should cater to the most frequent and important data operations. By doing so, we avoid bottlenecks and ensure smooth data flow. By considering data access patterns, we can ensure our database is not only well-structured, but also user-friendly and efficient. So, we've covered the key aspects of data design. We kicked things off by understanding how data requirements analysis sets the stage for the entire data design process. We then delved into the intricacies of conceptual and logical data modeling, where we identified high-level entities, attributes, and relationships, and translated these into a detailed representation. We also explored the twin processes of normalization and denormalization, each with its own unique role in organizing data and optimizing performance. We then navigated through the world of physical data modeling, where we saw how the logical model is mapped to physical storage structures. In addition, we understood the significance of data integrity constraints in maintaining data consistency and accuracy. Lastly, we touched upon data access patterns, highlighting how data design optimizes for common access and query requirements. And with that, you now have a fundamental understanding of how data is structured and organized in a database system. Thanks for watching.